August the 20th, 1942. Henderson Field, Guadalcanal. A Marine Corps engineer battalion worked under Japanese artillery fire, connecting steel panels across a muddy coral runway. 2 weeks earlier, this had been an unfinished Japanese airstrip. Now, American fighters were preparing to land. The Japanese commanders watching from the hills couldn't understand what they were seeing. Building an airfield required months, heavy equipment, massive concrete pours, engineering battalions working around the clock. The Marines had done it in 13 days. What those Japanese observers witnessed was a revolution in military logistics that Axis planners had never anticipated. A technology so simple it seemed almost absurd. Steel mats, perforated steel panels, delivered on trucks, unrolled like carpets. The Germans called it impossible when they finally learned of it. The Japanese had no comparable technology at all. By war's end, American aircraft were operating from locations that should have taken months to prepare. From coral atolls that could barely support vegetation. From muddy fields that turned into quagmires with each rainfall. From volcanic ash that conventional construction methods couldn't stabilize. This is the story of how American industrial ingenuity created a weapon that never fired a shot, yet helped win the war in both theaters. A weapon that shortened the Pacific campaign by months. A weapon that gave Allied forces operational flexibility Axis commanders couldn't match. The weapon was pierced steel planking, and it changed everything. In 1940, American military planners faced a problem that seemed insurmountable. Modern warfare demanded air superiority. Air superiority demanded airfields. Airfields demanded months of construction time. The German Blitzkrieg had demonstrated the importance of tactical air support. But German forces operated largely in Europe, where captured airfields were plentiful. France had hundreds of prepared airfields. Poland had dozens. Even the Soviet Union, despite its vast distances, had established air bases throughout its western territories. American planners looked at the Pacific and saw something very different. Thousands of islands, most without infrastructure of any kind, many without fresh water, some barely above sea level, and all of them separated by hundreds or thousands of miles of ocean. Traditional airfield construction followed a rigorous process. Survey the terrain, clear vegetation, grade the land, establish drainage, compact the soil, pour concrete or lay asphalt, wait for curing, install navigation aids. Timeline 4 to 6 months for a single airstrip. The U.S. Army Corps of Engineers calculated that island hopping across the Pacific at that pace would extend the war by years, possibly decades. Military planners understood the challenge clearly. The enemy would have evacuated or reinforced every position before Americans could make their airstrips operational. They needed a solution that was transportable, rapidly deployable, and functional on terrain that would normally be considered unsuitable. Axis intelligence, monitoring American communications about these logistical challenges, drew what seemed like a logical conclusion. The Americans would be forced to capture existing Japanese airfields. This meant the Americans would have to fight for every installation. Japanese defenders could prepare extensive fortifications. Each island would become a fortress. The strategic implication was clear. Fortify airfields. Make them expensive to capture. Slow the American advance to a crawl. Both Axis powers operated under the same assumption. Airfields were strategic choke points. Whoever controlled the airfields controlled the theater. What neither anticipated was that the Americans would simply ignore their airfields altogether. The solution came from an unlikely place: the Carnegie Illinois Steel Corporation. Engineers there had been experimenting with perforated steel decking for industrial applications. The perforation reduced weight while maintaining structural integrity. A solid steel plate strong enough to support heavy loads was too heavy to transport efficiently, but a perforated plate could achieve similar load-bearing capacity at a fraction of the weight. An Army engineer named Gerald Greulich saw potential military applications. As chief engineer at Carnegie Illinois Steel, Greulich held over 100 patents and understood structural engineering intimately. He proposed a system of interlocking steel planks, each 10 feet long and 15 inches wide. The planks would have holes punched through them in a specific pattern. The holes would reduce weight and allow water drainage. Most importantly, the planks would feature hooks along their edges that would lock adjacent panels together. The concept seemed simple, almost too simple. Military skeptics raised immediate objections. Steel would sink into soft ground. The perforation would create structural weak points. The interlocking mechanism would fail under stress. Aircraft landing gear would catch in the holes. Coral and volcanic rock would tear the panels apart. The Army Corps of Engineers conducted tests at Langley Field, Virginia, beginning in December 1939. Test 1. Load bearing. Engineers laid 200 panels over unprepared soil and drove a fully loaded B-17 bomber across the surface. Result: the planking supported the aircraft's 6,500-pound weight without visible deformation. Test 2. Weather resistance. Engineers subjected panels to simulated tropical conditions: high humidity, salt spray, extreme temperature fluctuations. Result: minimal corrosion after 6 months of exposure. Test 3. Rapid deployment. Engineers challenged a standard construction battalion to lay a 5,000-foot runway using the steel matting during field exercises in November 1941 at Marston, North Carolina. Basic hand tools only. Time to completion: 11 days for the first installation. One construction battalion, 11 days for their first attempt. A fully operational airstrip capable of handling heavy bombers. The town where this first practical deployment occurred gave the technology its name: Marston Mat. Named not after a person, but after Marston, North Carolina. The implications were immediately obvious to American planners. With experience, construction times would drop dramatically. The first combat deployment came sooner than anyone expected. Bluey West 1 Airfield in Greenland. Construction began in fall 1941 in brutal Arctic conditions. The first aircraft landed on January 24, 1942. Greenland proved the concept worked in extreme environments. But the Pacific would demonstrate its true strategic value. Meanwhile, American production ramped up. By January 1943, U.S. steel mills were producing pierced steel planking at a rate approaching 1 million square feet per month. The mats came in standardized panels, packaged for ocean transport, ready for immediate deployment. Each panel weighed 66 pounds, light enough for 2 men to carry, strong enough to support a P-51 Mustang. A standard C-47 transport could carry approximately 74 panels, enough to create over 1,100 square feet of runway surface. Land the aircraft, unload the panels, have an engineering team lay them out, take off again, all within 6 hours. The real revelation came with scaling. A single Liberty ship could carry enough matting to construct a 5,000-foot runway with parallel taxiways and dispersal areas. Total material, approximately 2 million pounds of steel. Total deck space required, less than 1/3 of the ship's capacity. This meant each transport convoy could carry not just troops and supplies, but entire airfields. Deployable on arrival, operational within days. The Pacific test came in August 1942, Guadalcanal. Henderson Field had been a Japanese construction project, abandoned incomplete when Marines landed on August 7th. The airfield was a primitive coral strip that turned into a muddy morass during the frequent tropical downpours. Aircraft bogged down. Takeoffs became hazardous. Operations would have ceased entirely during heavy rain without intervention. The 1st Marine Engineer Battalion, working alongside the 6th Naval Construction Battalion, had steel matting available from the initial landing supplies. They began laying panels over the existing coral surface. No additional grading, no foundation preparation, just interlocking steel panels connected by their edge hooks. Marine engineers worked in teams of 4 under artillery fire. 2 would position the panel. 2 would lock it to adjacent panels using simple hand hooks. They maintained a pace of approximately 500 panels per hour when not taking cover from Japanese shelling. The runway was operational in 13 days. More importantly, it remained operational during the next rainstorm. Water drained through the perforations. The steel surface provided consistent traction. Aircraft could operate regardless of weather conditions. Japanese commanders monitoring Henderson Field noticed the change immediately. American air operations continued regardless of rain. What had been a vulnerable choke point became a reliable base of operations. The strategic implications were profound. Traditional airfield construction created predictable patterns. Intelligence could identify construction activity from aerial reconnaissance, survey teams, heavy equipment, extensive ground preparation. These activities were visible from altitude days or weeks before an airfield became operational. Defenders could anticipate where American aircraft would operate and position forces accordingly. Marston Matt changed the equation completely. Aerial reconnaissance might show trucks, perhaps some organized activity, but no obvious signs of airfield construction. No concrete mixers, no grading equipment, no months-long timeline that telegraphed American intentions. The intelligence advantage shifted dramatically. American forces could select landing zones based on tactical requirements rather than existing infrastructure. They could establish air support within days of securing a beachhead. They could abandon airfields that came under pressure and rebuild elsewhere with the same materials. The Pacific Island hopping campaign demonstrated this flexibility in operation after operation. Tarawa, November 1943. Marines secured the island after 76 hours of intense combat. Aviation engineers landed with early waves of troops, bringing steel matting in landing craft. Before the island was fully secured, they had begun laying runway panels over the damaged Japanese airstrip. American fighters were operating from Tarawa within 96 hours of the first Marines hitting the beach. Japanese military planners had assumed Tarawa's capture would deny Americans an operational airfield for weeks. The existing runway had been deliberately damaged. Repair would require extensive reconstruction, or so they calculated. Kwajalein, February 1944. The atoll consisted largely of coral, soft coral, material that would never support conventional runway construction. American engineers laid 6,000 feet of matting directly onto the coral surface. Heavy bombers were operating from Kwajalein within a week of its capture. Saipan, June 1944. Japanese defenders had destroyed existing airfield infrastructure during their retreat. Runways cratered, buildings demolished, support facilities burned. American engineers covered the damage with steel matting. The airfield was operational before the island was fully secured. The pattern repeated across the Pacific. Each island the Americans took became an air base. Not eventually, immediately. Japanese defensive doctrine had assumed American advances would be constrained by logistics. That assumption proved fatally incorrect. The technology found applications beyond the Pacific theater. In North Africa, engineers used steel matting to create airfields in desert sand that conventional runways would have taken months to stabilize. British and American forces could establish tactical airfields within days, supporting mobile armored operations. In Italy, matting covered muddy fields that turned to soup during the winter rains. Allied bombers maintained operations against German positions regardless of weather. Luftwaffe planners had counted on winter conditions to reduce Allied air activity. The steel mats eliminated that advantage. After D-Day, engineering battalions landed on Normandy beaches with steel matting in their equipment manifests. Within 72 hours, fighters were operating from French soil, not from captured airfields, from fields that had been pastures the previous week. German defenders watching Allied operations from a distance struggled to understand what they were seeing. Fighter aircraft taking off from locations that showed no signs of airfield construction. Bomber formations staging from areas that appeared to be ordinary fields. The reconnaissance photos showed trucks and activity, but no infrastructure. The production numbers tell the story of American industrial capacity. Between 1942 and 1945, US manufacturers produced approximately 2 million tons of pierced steel planking, enough to construct roughly 954 miles of runway, enough to cover an area equivalent to several dozen major airfields. Weight of material, 2 million tons of steel. By comparison, this represented a significant portion of American steel production dedicated to a single logistical innovation. Cost per panel, approximately $3.31 in 1943. Cost of conventional airfield construction, $2 to $5 million. A complete mast and mat airfield, including all materials and labor, approximately $200,000 in materials alone. 1/10 the cost, operational in 1/30 the time. Historical records indicate neither Germany nor Japan developed comparable technology during the war. Air and Space Forces magazine's research concluded that both Axis powers had nothing remotely similar to American pierced steel planking. German logistics were rail-based. The matting worked best with truck-based logistics that could deliver materials directly to remote sites. German forces lacked the motor transport capacity to distribute matting effectively, even if they had developed it. More critically, by the time the technology's importance became clear, Germany was fighting defensively. Rapid airfield construction made sense for an advancing force. For defenders falling back, existing airfields were plentiful. The problem wasn't building new airfields, it was defending the ones they had. Japanese industrial capacity couldn't support large-scale matting production while simultaneously maintaining military aircraft and naval vessel construction. Even if Japanese engineers had developed workable prototypes, American forces controlled the sea lanes necessary to transport materials between islands by mid-1944. Axis response to American steel matting essentially defaulted to trying to destroy it after it was already in place. Japanese artillery targeted matted runways. Luftwaffe bombers cratered Allied airstrips. Both discovered that steel matting was surprisingly difficult to disable permanently. Conventional runways, when damaged, required extensive repair. Bomb craters had to be filled. Concrete had to be poured. Curing time was required before the surface could handle traffic again. A well-placed bomb could shut down a concrete runway for days or weeks. Matted runways were different. Bomb damage might destroy a few panels. Engineers would simply disconnect the damaged sections and install replacements. Typical repair time 4 to 6 hours. American engineering manuals from the period noted that a 500-pound bomb direct hit on Marston Mat runway typically damaged an area approximately 20 feet in diameter. Replacing damaged panels required removing and installing approximately 40 panels. With a 4-man crew, this operation typically required less than 3 hours. The runway returned to full operational status immediately. The operational flexibility extended beyond simple construction speed. Matted airfields could be expanded or reconfigured with minimal effort. Need a longer runway. Add more panels to the existing strip. Need additional parking areas. Lay panels adjacent to the main runway. Need to relocate the entire airfield. Disconnect the panels, load them on trucks, and rebuild elsewhere. American forces exploited this flexibility repeatedly. In the Philippines, engineers relocated entire airfield complexes 3 times during the campaign, moving with advancing infantry to maintain close air support throughout operations. In New Guinea, matted runways expanded progressively as bomber ranges required longer takeoff distances. Initial installations might be 3,000 feet. Engineers would extend them to 5,000 feet as heavier aircraft arrived, then to 7,000 feet for B-24 operations, all without shutting down ongoing operations. The environmental versatility proved equally valuable. Steel matting functioned on surfaces that conventional construction couldn't address. Coral atolls. The panels distributed weight sufficiently to prevent sinking into soft coral. Conventional runways required coral crushing and extensive compaction. Marston Mat worked directly on the surface. Volcanic ash. In areas like the Pacific Islands with volcanic soil, the matting created a structural layer that spanned unstable substrate. Permafrost. In Alaska and northern regions, freeze-thaw cycles destroyed conventional runways. The flexible steel panels accommodated ground movement without structural failure. Jungle environments. Heavy tropical rainfall turned dirt airstrips into impassable mud. The matting provided drainage through its perforations while maintaining a solid surface. Desert sand. Wind-blown sand accumulated in drifts that buried conventional runways. The perforated design allowed wind to pass through, reducing drift accumulation. Each environment presented unique challenges. Traditional construction methods required different solutions for each. Steel matting worked in all of them. The human element of the story reveals itself in the experiences of engineering battalions who installed matting under combat conditions. These units operated at the intersection of logistics and warfare, working in environments where the enemy might still be present. Engineers described working in rotation, maintaining 24-hour installation schedules. Panels were pre-staged in stacks near work sites to minimize transport time under fire. Installation crews wore full combat gear, ready to take cover if enemy fire intensified. Some units reported laying matting while under direct small arms fire, using bulldozers as mobile cover. Casualties among engineering units were significant. The 1892nd Engineer Aviation Battalion, an all-African-American unit, suffered casualties during the Okinawa campaign, primarily from artillery fire while constructing airfields. Engineering work in combat zones was dangerous work. Yet the matting got laid. The airfields became operational, and tactical air support arrived days or weeks ahead of schedule. The psychological impact on enemy forces was substantial. Japanese defenders on isolated island garrisons understood that American air superiority meant inevitable defeat. What they hadn't anticipated was how quickly that air superiority would arrive. Islands they expected to defend for months came under sustained air attack within a week of American landings. Captured Japanese officers interviewed after various island campaigns consistently expressed surprise at the speed of American airfield construction. They had calculated defensive strategies based on conventional engineering timelines. When reality contradicted those calculations by an order of magnitude, it undermined confidence in all strategic assessments. The matting's success created unexpected secondary effects. American tactical doctrine evolved to exploit rapid airfield construction. Operations that would have been considered logistically impossible became standard practice. Marine Corps. Amphibious doctrine was rewritten to assume close air support would be available within 48 to 72 hours of a landing, rather than weeks. This changed assault planning fundamentally. Marines could land with lighter artillery, knowing that air support would arrive quickly to provide heavy fire support. This allowed faster landing schedules and reduced the logistical burden on initial waves. Army Air Force targeting doctrines adapted to the reality that forward airfields could be established almost anywhere. Fighter groups could deploy to support ground operations without waiting for engineers to complete conventional airfield construction. This meant tactical air power could respond to ground force needs in days rather than months. Strategic bombing campaigns benefited similarly. As Allied forces advanced across Europe and the Pacific, bomber ranges to target areas decreased because forward airfields appeared rapidly. B-17s operating from England had to fly hundreds of miles to reach German industrial targets. B-17s operating from hastily constructed matted airfields in France or Belgium cut mission distances by half. This reduced fuel requirements, increased bomb loads, and decreased crew fatigue. The economic implications extended beyond simple cost savings. Traditional airfield construction required specialized cement, asphalt, and heavy construction machinery. These resources were globally scarce during wartime. Steel matting used relatively common materials that could be produced by facilities across the United States. This distributed production meant the program wasn't bottlenecked by specialized suppliers. Labor requirements dropped dramatically. A conventional airfield might require 500 skilled construction workers laboring for 6 months. A matted airfield required 100 combat engineers working for 3 days once they gained experience. Those 500 skilled construction workers could be deployed on other projects. The combat engineers moved with the advancing front, installing airfields as they went. Transport efficiency created additional advantages. Concrete and asphalt required specialized transport ships with appropriate storage conditions. Steel matting could be loaded onto any cargo vessel. It could even be transported on returning Liberty ships that had delivered troops and supplies, utilizing otherwise empty cargo space. This efficiency meant that the logistics tail for airfield construction effectively disappeared. By 1945, the technology had become so routine that American forces took it for granted. Matted airfields appeared wherever operations required them. The extraordinary had become ordinary. After the war ended, Marston Mat found new applications. The Berlin airlift in 1948 initially relied on matted runways at Tempelhof Airport, though these proved inadequate for the heavy C-54 Skymasters and required replacement with asphalt between July and October 1948. Korea saw extensive use of steel matting throughout the conflict, with nearly 30 million square feet deployed on airfields. Vietnam featured hundreds of thousands of tons laid throughout South Vietnam, with improved variants developed to minimize damage and vegetation issues. The technology that helped win World War II continued serving American forces for decades. Modern military engineering still uses descendants of the original Marston mat design. The materials have evolved. Aluminum replaced steel to reduce weight. Composite materials offer even better performance, but the fundamental concept remains unchanged. Portable, rapidly deployable runway surfaces that function on unprepared terrain. The legacy extends beyond military applications. Construction matting based on World War II designs supports heavy equipment on soft ground at civilian construction sites. Temporary roadways for emergency access use similar principles. Even temporary event surfaces for outdoor festivals derive from military matting concepts. But the wartime impact remains the most significant. A technology that Axis planners couldn't replicate. That accelerated Allied victory by months or perhaps years. Hugh Casey, who served as chief engineer of U.S. Army forces in the Pacific under MacArthur, later contributed to the official history Engineers of the Southwest Pacific, published in 1947. The multi-volume work documented that victory in the Pacific rested as much on pierced steel planking as on any weapon system. Allied forces didn't just outfight the Japanese. They out-engineered them. They created airfields faster than the enemy could respond. They established air superiority, not just through better aircraft, but through better logistics. The matting was the foundation of that superiority. The perforated steel panels that rolled off American production lines by the millions represented more than engineering. Innovation. They represented a fundamental difference in how America approached industrial warfare. Axis military planning focused on weapons, better tanks, better aircraft, better artillery. American planning focused on systems, not just the weapons, but the infrastructure to deliver them where needed, when needed. Pierced steel planking wasn't glamorous. It didn't feature in dramatic battle reports. Few medals were awarded for laying matting. But it enabled everything else. Every fighter that took off from a forward airfield to support ground troops. Every bomber that reduced its mission distance by operating from an advanced base. Every casualty evacuated from a field hospital by aircraft landing on a matted strip. All of it depended on steel panels laid by combat engineers working under fire. The Marines working at Henderson Field in August 1942 demonstrated something that would prove decisive. American engineers had imagined differently. They imagined runways that could be delivered on trucks, airfields that could be operational in days, infrastructure that moved with the front lines. They turned that imagination into 2 million tons of perforated steel, into nearly 1,000 miles of runway, into air superiority across 2 oceans and 3 continents. The steel mats rusted eventually. The airfields were abandoned or paved over. The engineering battalions went home. But the principle endured. Victory in modern warfare belongs not just to whoever fields the best weapons, but to whoever can field those weapons where they're needed, when they're needed. Axis planners never imagined American engineers would unroll airstrips from trucks. That failure of imagination proved decisive. Sometimes wars are won not with weapons but with logistics. Not through destruction but through construction. Not by outfighting the enemy but by out-engineering them. 2 million tons of perforated steel proved that principle beyond doubt.